Welcome everybody. Sorry about the late start. Little technical difficulties this morning. This is the third of our series of Saturday seminars. It's a loosely produced series of netcast seminars in cooperation with the Fireworks Foundation, the Pyrotechnics Guild International, the Western Pyrotechnic Association. These seminars are being put together to help give our pyrotechnic community around the world something to stay engaged with while we're in this unusual time at home and unable to carry on our usual activities. I'm Steve Wilson. I'm one of the founding members of the Western Pyrotechnic Association and currently the seminar chairman for the WPA and the Pyrotechnics Guild International. I'd like to take a moment to acknowledge our team here this morning, which includes Brooke Roselle and Mike Garrett, our production assistants, and Joe Wright, who's running the technical part of our streaming. And I'm really happy to have these guys on board. Okay, these seminars are for educational purposes only. We suggest that anybody interested in amateur pyrotechnics join a local or regional club and gain the proper education and mentoring. Never attempt things that you don't know enough about. It's responsibility of the viewer to make sure that they're in compliance with all federal, state, local laws, that kind of thing. During this seminar, you're going to be encouraged to ask some questions later on as you feel fit. Those of you viewing in Zoom webinar may use the Q&A feature at the bottom of the screen. Those on Facebook may enter the questions in the comment box, and we'll try to transcribe those into the Q&A where one of our moderators, Brooke or Mike, can ask Bob those questions when it's appropriate. A little bit about Bob Winokur. Bob is very well known around the world. His most famous work is in Pyrotechnica 2, the business about glitter. And incidentally, I've got a few of these for sale at the end of the seminar. There's an email address, and if you want to get one of these, they're $25 plus shipping. Bob has been a professor at UNLV, that's the University of Nevada at Las Vegas, for a long time. His actual career was a professor of zoology, and he's been a PGI member since 1971. He was president in the 1980s. He's been a frequent contributor of the PGI Bulletin and ran a display company in Las Vegas. And Bob has also given many, many seminars at our conventions, both the WPA's, Western Pyrotechnic Association, and the PGI. And Bob was a big help in helping us get these seminar series going by doing our first remote webcast at Western Winter Blast this year. So without any further ado, I'd like to introduce Bob Winokur, and we're going to switch over to his screen. And you can go ahead and start talking anytime, Bob, and then you guys want to talk him through getting the screen up.
Okay.
Good morning, Bob.
Today, I'm going to give a seminar that I gave a couple of years ago that I revised. And this was a seminar I gave at the WPA. But it's on the topic of, are fireworks poisonous? And this is a subject that comes up quite a bit, and there's a lot of misinformation out there and a lot of official documents from state agencies and sometimes even federal agencies, which are quite simply wrong. And I wanted to spend a little time clarifying these and providing a way of thinking about toxicity. So they're set up so questions can be asked, and I will deal with them to the best of my ability, but feel free to ask questions whenever they come to mind. Okay, well, can I get started with the seminar, Steve?
Yes, go ahead and go to your share screen, Bob.
How do I do that?
You're going to take that cursor, you're going to scroll it down to that little green box that says share screen at the bottom of your screen.
It's not there.
Not there. Okay.
Well, there it is.
So go ahead and click that. And when you see your presentation, go ahead and click on your presentation.
Okay, it's there. My screen is covered with the people talking, however.
They're not able to be viewed by the audience. So go ahead and go to full screen.
I didn't change anything.
Okay, no worries. So go to where it says May 2020 on your screen.
Yeah.
With your cursor, you're going to drag that cursor down to where you see that little projection icon at the bottom of your screen. So go ahead and drag that cursor all the way straight down. You'll see what looks like a little book at the bottom. To the right of that, go ahead and click on that little icon. Okay, there you go.
Okay. Now, but the pictures of the four of you are still on my screen, blocking my screen.
They're visible to you, but they're not visible to the audience. And you can do that by minimizing us. So if you go to the top of the box where you see our pictures, you're going to see two blue squares on top of each other, or rectangles on top of each other, a solid white rectangle in the center, and then a little tiny dash line. Go ahead and click that dash line.
There it goes.
Okay.
Bingo.
All right, you're ready to go.
Now I'm ready to talk, right?
You're ready.
All right. Sorry for this delay, folks, but this is the first time some of us have done this. So the title of my talk is Are Fireworks Poisonous? And it turns out that's a complex question. It's one that has to be qualified and a little hand waving here and there. And, but I think it's an important one because it's on a lot of people's minds. And so we'll go to the next slide. The answer to the question depends on how one defines what is poisonous. Now, most people have a pretty clear idea of what we mean by being poisonous, but in fact, it's not an easy question. Ordinarily, it's thought of materials that can result in death or severe illness from ingesting a few milligrams or less. Others, of course, take considerably more than a few grams. Some commonly ingested non-poisonous substances can be lethal if ingested in excess. For example, ordinary water or sodium chloride, table salt. And we don't think of water or table salt as poisonous, but if you eat enough of it, it can kill you. All right, so dosage is really important. So poisons are often characterized by noting what's called the LD50, referring to lethal dose 50%, meaning that 50% of the individuals tested die from the administered dose. Now, LD50 is not as commonly used as it used to be, but the way it was studied is they would give rats or mice a whole series of doses and find out what dose ended up killing them, killing 50% of the population that was tested. LD50 is usually expressed in milligrams per kilogram of body weight. So, you know, if you're a 150 pound person versus a 200 pound person, it's going to take more chemical to kill you. There are 1,000 milligrams in a kilogram. 500 milligrams equals about a half a gram, to give you a concept. A 150 pound person weighs a little over 68 kilograms. So an LD50 of 100 milligrams per kilogram would mean that a 150 pound person would have to ingest 6,800 milligrams, or 6.8 grams, or about 1/4 of an ounce, to have a 50% chance of dying. So it's not a simple matter of is it poisonous or is it not. That depends on how much you take and how much you weigh. Now, in a particular example, the legal limit for flash powder in a common Chinese consumer grade firecracker, as pictured here, in the US is a 50 milligram or 1/10 of a gram of powder. And here we see a picture showing a Chinese firecracker opened up with the powder spilled out. Now, this may not seem like much, but it is effective in making a sharp report. And so here's what 50 milligrams of flash powder looks like. Now, that's a long way from 6.8 grams to 1/10 of a gram. Now, toxicology has been around for a long time. The founder of toxicology was Paracelsus, and he lived in the from 1493 to into the 1500s. And he said, all substances are poisons. There are none which are not poison. And that's an interesting thing to say. Because if you eat enough of anything, it can be poisonous. Now, we usually don't think of poisons in that regard, but it is true, and you have to think about it in terms of dosage. There are two distinct kinds of poison exposure are commonly recognized. Two distinct kinds of poison exposure are commonly recognized. There's acute exposure, where a single exposure to a toxic substance may result in severe biological harm or death. And acute exposure is usually characterized by lasting no longer than a day. So when you have an acute exposure, if you don't die in the first day, you're probably not going to die. And then there's chronic exposure, continuous exposure to toxins over an extended period of time, often measured in months or years. Some are cumulative and remain in the body. They're sometimes stored in fat, for example. And others can cause irreversible damage to organs and tissues. So there's a difference between acute exposure and chronic exposure. Now, there are a large number of significantly toxic plants commonly found in our environment. And we easily survive by applying a simple rule: don't eat them. Amanita muscaria is a mushroom that's quite common in the United States. And it's beautiful, and it's deadly. And sago palms, common decorative things. If you eat enough sago palm, it can kill you. Poison ivy and poison oak. This is a picture of poison ivy. It's a very common herb. It's poisonous to the touch and potentially lethal if you eat it, ingest it, or you burn it and inhale it. And so, you know, poison ivy grows in lots of people's backyards. And if you take a walk in where I grew up in Minnesota, poison ivy is very, very common. But you don't hear of people dying from it, from eating it, because they know better. Oleander, commonly grown around homes, is very toxic. But you don't hear about people dying from oleander because they have enough sense not to eat it. So let's talk about chemophobia. It's one of my favorite topics, actually. Let's define it. Chemophobia is an attitude towards chemicals largely derived from fear and ignorance that convinces people that chemicals are inherently dangerous. In short, chemicals are bad. A clear signpost of chemophobic thinking can commonly be found in the writings of a lot of people who compose warnings about poisons. They say such things as, this composition or product is laced with XYZ, is a common expression. There is a studied ignoring of dose effects, characteristic of many assertions about the hazards of using some substances. Typically, a long list of devastating symptoms are listed with no doses provided to give the impression that the substances are especially dangerous. And it's easy to find such warnings. Well, the origins of chemophobia they are from several sources. The most prominent one is simple chemical unfamiliarity coupled with substantial ignorance about chemicals. Chemistry is so often poorly taught in our primary and secondary schools, and our colleges, I might add, and possessing or handling anything perceived as toxic is usually prohibited. In many grade schools, even an open flame is commonly prohibited. It is sometimes against the rule for a teacher to light a Bunsen burner or an alcohol lamp or even a candle. The outcomes of this is a result of people do not learn what it means to be careful. So we often hear in pyrotechnics, people say, well, you be careful when you do this, but that assumes that a person understands what it means to be careful, but our education about chemicals prevents that. And this attitude feeds upon itself in an interesting way. Each new regulator is motivated to institute new and increasingly rigorous regulations. So a regulator writing 20 years ago or 30 years ago will have said something, but a modern regulator will read what they say and they say, well, we're going to do better than that. And better usually means more rigorous regulations. Education in chemistry, even sometimes at the college level, can be largely or nearly devoid of actual chemicals. It consists mainly of learning to work problems. Classical chemical knowledge has unfortunately sometimes been labeled derogatorily as descriptive chemistry. To mail a poison or a flammable solid through the US mail demands enormous precautions and great expense. So chemophobia can be very expensive. All right, now, here we see a list of some chemicals that are, common poisons. And I listed the chemicals that are used in pyrotechnics in red, and a few that are not used in pyrotechnics in black. So aspirin, and notice here's an LD50. So to kill a rat, you need 200 milligrams per kilogram of rat. Aspirin, of course, is commonly used for pain control. Arsenic oxide. This is the common arsenic that is used as rat poison. And you notice its LD50 is a lot less than aspirin, 15 milligrams or 20 milligrams in the case of a mouse. Now, arsenic tetrasulfide, sometimes it's called the tetraarsenic tetrasulfide because it's got 4 arsenics and 4 sulfides. And it's 185 milligrams per kilogram. It's rarely used and is banned in consumer fireworks. Barium nitrate, commonly used in fireworks. It produces green fire and it's used in sparklers. And it's one of the few really common poisonous chemicals that are used in fireworks. Barium chlorate is used uncommonly. It's mainly used in display fireworks stars. It produces a really striking green flame. And but it's soluble barium, and soluble barium is poisonous. I list caffeine, which is something we ingest, many people ingest daily. It's found in coffee, of course, and in a variety of soft drinks. Cyanide, everyone's heard of potassium cyanide. And notice its LD50 is really small, 4 to 6 milligrams per kilogram. And it's used in animal control, and it's not used in fireworks. Dendrotoxin, snake venom. You can eat a lot of it, but you don't want to get it injected into you. You can't eat a lot of it. It's pretty deadly stuff. And then there's ethyl alcohol, or grain alcohol. It has a huge LD50, but it results in more deaths than anything on this page. So, just because of something poisonous doesn't necessarily mean it is extremely dangerous. Paris green, copper acetoarsenite, no longer commercially available and no longer used, but it was a common ingredient in the first half of the 20th century. Strychnine, a complex alkaloid used in bird and rodent control, not used in fireworks. And white phosphorus, look at the LD50, 3.2 milligrams. That's just a tiny bit of white phosphorus. But white phosphorus is banned and no longer used in the US, but may occasionally be found in Europe and some third world countries where it's not banned. But white phosphorus is simply too reactive. It's not used in fireworks as a general rule, certainly not in the United States. Caffeine, pretty toxic if you take enough of it. Here's Paris green, I mentioned it. It was used in pyrotechnics to produce blue and purple flames. It's perhaps the most famous poison used in fireworks. It was originally manufactured as a pigment and later utilized as a pesticide. It has an LD50 of 18 to 22 milligrams per kilogram. One could easily purchase it in the US throughout most of the 20th century. You go to any hardware store back in the first half of the 20th century, and you can find Paris green for use in your tomato patch. They quit manufacturing it in the 1960s for agriculture, and it is largely unavailable today. Realgar, tetraarsenic tetrasulfide, AS4S4. Used to be called AS2S2, and you'll even see some of the older literature listing its formula as just ASS. This is a naturally occurring mineral, today used very rarely in fireworks. It was used in smokes and white stars, and the Japanese use it in special dark fires layered between color compositions and color changing stars. So when you see a chrysanthemum break, you often don't see red, green, and green. What you see is red, and then all the red seems to go out, and then the green comes on. And those are called changing relays. Now, it's not hard to buy Realgar in quantity. It's available in China. It's not used in the West very much anymore. And it's banned in US consumer fireworks. It's a very pretty mineral. Here it is in a powdered form. Here it is in a natural mineral. It is water insoluble, which limits its toxicity to a degree. When Realgar crystals are exposed to light for an extended period, a photochemical reaction takes place, and the bright red Realgar that you see here changes to a somewhat structurally but chemically identical yellow powdery mineral called para-realgar. So if you have some realgar crystals like this around for a while, they start to look like this. This has given rise to an incorrect belief that realgar is changed into orpiment, which is a yellow arsenic sulfide. Para-realgar appears like this frost-like covering that accumulates on the surface of light-exposed realgar. Para-realgar was not understood by mineralogists until the 1980s. So you can forgive mineralogists from thinking that orpiment was produced by realgar, but it is not. All these minerals are poisonous, but how poisonous? Well, they're both water insoluble, both realgar and para-realgar, and they have relatively low bioavailability. However, you have to have caution because when you ingest these things, they get into your stomach and they're exposed to stomach acid and such. So you can be poisoned by realgar, but you have to do more than touch it or eat a tiny fragment of a crystal. Now, arsenic trisulfide orpiment is another poisonous thing that's been used in fireworks. It's rarely used today. It is banned in U.S. consumer fireworks. Orpiment now finds virtually no uses in modern fireworks, although it had been utilized occasionally in smokes and flower pot fountains made in the early 20th century. It's found naturally. It has to be ground up, but it's not readily available and certainly not used today. Now, here's an important point. Ingesting excessive amounts of table salt can be fatal. If you ingest 47 teaspoons of table salt all at one time, it could be fatal. If you want to ingest a lot of sodium or potassium, eat 480 bananas at one time. That's not likely, is it? But even bananas could be poisonous.
Excuse me a second, Bob. This is Steve. I just wanted to let you know that we had a number of people that came in late. There were some technical difficulties with some of our logons. So those people are on now, but I just want to let you all know this is Bob Winokur, and it's a seminar on our fireworks are poisonous. And you might want to, if you could just recap very quickly where we got up to at this point and then continue on.
All right, I'll tell you what I'll do. I'm going to look at, to answer the question, are fireworks poisonous? Well, you have to answer what it means to be poisonous. Well, a lot of things that are poisonous, and I talked about dosages, and that's important. And here's what open the firecracker, and you see what the firecracker contains. And so there's 50 milligrams of flash powder. And that's not a lethal dose by any means of flash powder. I mentioned Paracelsus, founder of toxicology, who claimed all substances are poisons. There are none that which are not poison. That's interesting. Acute exposure versus chronic exposure. I discussed that. I gave a picture of Amanita muscaria and sago plant, both common plants in the United States. They're very deadly. But there's a simple rule, and we survive them by following the simple rule. Don't eat them. Poison ivy, real common herb. Very toxic, especially if ingested or burned. Oleander, grown around households, very poisonous. I talked about chemophobia, and you can read this at your leisure. And then this is an important table where I go through some of the common chemicals that have been or are used in fireworks. Barium nitrate, barium chlorate are common used chemicals in fireworks. Barium chlorate is much less used because it's more expensive and has so few uses outside of pyrotechnics, but it's used in display fireworks for stars. Chlorates are banned in Class C fireworks, but barium nitrate is found in sparklers, in green stars, and green flares and lances and so on. I pointed out that ethyl alcohol results in more deaths than anything on this page. So when you talk about poisons, you have to qualify your discussion. Caffeine is poisonous. Many of us take it every day. I talked about Paris green, copper acetoarsenite, commonly used in the first half of the 20th century, no longer manufactured, not readily available. Realgar, tetraarsenic tetrasulfide, again, not used. And when realgar is exposed to light, one sees this yellow frosty material, which is called pararealgar. And it's a form of realgar. It's structurally somewhat different, but chemically it's still realgar. Arsenic trisulfide, orpiment, another arsenic compound no longer used in fireworks. Now, the dose thing is important. Table salt. If you eat enough of it, it can be fatal. 47 teaspoons of table salt can be fatal. You could eat 480 bananas, and that would be fatal. I've never heard of anyone dying from eating 480 bananas, but it would be possible. Water and toothpaste, if you eat enough of them, can be fatal. So how is toxicity defined? Well, it's defined as the degree to which a substance can cause harm or death. So if something is a little bit toxic, you have to eat a lot of it. If it's very toxic, you only have to eat a little bit. The central concept of toxicology is it is dose dependent. And that's why even water can lead to water intoxication or death when taking too high a dose. Even very toxic substances such as snake venom, there is a dose which there's no detectable effect. So even the most toxic substances, if you eat just the tiniest quantity, it doesn't kill you. Another thing that complicates this question is toxicity is species specific. So what might be poisonous to a horse may not be poisonous to you. And sensitivity to toxic substances are also individually variable. And this is a really difficult bugaboo because individual people are variable regarding to how much of a dosage that they can experience. Human variability is something I like to talk about. It's a fundamental and extremely important concept, and it applies to this subject of toxicity. Humans are intrinsically and extremely variable. And if that sounds like something a biologist would say, you're right. This variation is not only in appearance and anatomy, but sensitivity to drugs and poisons. What is a safe level exposure in one individual may be dangerous for another. We can make fairly good approximations, but we must be cautious of understating or overstating the dangers. Either can result in negative outcomes. Human variability is very real, and I put together these pictures to illustrate how variable humans are. I wanted to point out, note this little boy has a tail. And this is a fairly recently born child. And Robert Wadlow was 8 feet 11 inches tall. So we're so accustomed to seeing variable. If two people look much alike, we assume they're related. And if we walk down the street and notice that everybody looks a little different, we're so accustomed to that it doesn't fall into our consciousness. But this variability affects toxicity. Some common poisons in our kitchen and homes. You don't hear anybody getting too upset about cherry pits or peach pits or apple seeds. They're all toxic. You might have to eat quite a bit of them, but if you crack open a cherry pit and eat the little seed inside, guess what it contains? Cyanide. Tomato leaves and stems are toxic. Rhubarb leaves are toxic. Castor beans, we don't eat them, but they are grown decoratively and they contain a really deadly poison called ricin. Oleander flowers and leaves that I've already pictured, daffodil flowers. So we are surrounded by poisons all the time. Now, firecrackers and other exploding fireworks commonly contain potassium chloride. The lethal dose for humans is 5 to 35 grams per kilogram. Well, 5 grams is quite a bit. The average firecracker only has 50 milligrams. So if you look at potassium chloride, the heads of about 20 wooden matches or 2 books of paper matches is not enough to be harmful if ingested by a child. And safety match heads do not contain phosphorus. And you can find a lot of misinformation in the literature saying matches contain phosphorus. Well, in fact, they used to around the turn of the century. They made strike anywhere matches with yellow phosphorus, but that was banned around the turn of the century. So today, flash powders contain about 50 to 70% potassium chloride. So a 50 milligram firecracker would not contain more than 35 milligrams of potassium chloride, well below a harmful dose. Now, that doesn't mean you should eat firecrackers, of course, but they're not poisonous. Now, let's look at some other chemicals. Fentanyl is an opioid compound commonly used in medicine. A lethal dose looks like that. Okay? Here's a lethal dose of heroin. Here's a lethal dose of fentanyl. So these are substances that are used routinely in medicine. So if you make fireworks and you handle chemicals, there are some things you should know how to do. How to wash your hands. How to use gloves. Little disposable gloves like this are quite handy. Wearing a face mask. When I made the seminar, nobody was wearing face masks, but since the advent of the coronavirus, this is a common thing now. And there are other kinds of masks you can wear that will help you from inhaling chemical dusts. I like lava soap hand cleaner. It's especially good at cleaning hands. If you have hands that look like this, you can use regular soap and it doesn't necessarily do a good job. But lava soap does. But you don't want to wash your hands 3 times a day or 4 times a day with lava soap. You're going to give you rough skin. But it's very effective, once or twice a day to use if you're making fireworks.
Hey, Bob, we had a comment a little bit earlier when you had the slide up with all of the various chemicals, and white phosphorus was on the list. Came from a Facebook participant, and they mentioned that they wanted to clarify that the European standards for fireworks prohibit the use of white phosphorus or phosphor. But if you find it, it's likely to be an old stock or possibly collector's items. Do you have any comments on that? Or?
Well, certainly in Europe, which has pretty good fireworks regulations, they don't use phosphorus. But Turkey, for example, has used yellow phosphorus in some items, and so we don't think of Turkey as a European country. I agree, but it does show up from time to time, and it is, you know, you're not going to find it in Europe commonly, certainly. And it is not a concern. It hasn't been a source of toxicity for over 100 years in fireworks. All right. So, lava soap, I like it. That's one friend of mine recently pointed out that if you're using lampblack, which is extremely messy stuff to use, and it gets on your hands, it doesn't come off, mayonnaise. And he mentioned the mayonnaise that has horseradish in it is very effective in removing lampblack. So if you use lampblack, that would be a good thing to know about. If you don't make fireworks, would like to use them, try not to eat them or give them to toddlers that are mentally ill. This is obvious, but you listen to some regulators, they make it sound like fireworks are a common source of poisoning. In fact, they are not. Let's look at some harmful effects of chemicals used. Now, this is a document, and I hope it's not typical, but this document came from the New Hampshire Department of Environmental Sciences, Environmental Services, published in 2008. So it's a relatively old document, but it's listed here in black. So when the black writing is what the New Hampshire document says, and the red printing is my comments. So let's look at some of these. Copper, poison to humans by ingestion. Inhalation of copper dust causes irritation to the respiratory tract. Absorption of excess copper results in Wilson's disease, in which excess copper is deposited in the brain, liver, pancreas, and myocardium, the middle muscle layer of the heart. That sounds pretty dire. The fact is that elemental copper is not used in fireworks. It's too easily reacts with other chemicals. It's not used. And copper salts are used only in blue-colored flames and represent only a tiny source of copper in our environment. Copper plumbing is common even today. We touch pennies made of copper daily. And in fact, copper is an essential nutrient. Wilson's disease is a rare genetic condition and exposes copper. And exposure to copper is not the cause of Wilson's disease, but causes copper to collect in some of those rare individuals with Wilson's disease that are exposed to copper. So the writer of this paragraph badly misunderstood what was going on. Now this really annoys me. Cadmium. Well, cadmium can be poison to humans, ingestion, intravenereal, and they go on and on about cadmium. Well, the fact is, toxic. It's never been used in consumer fireworks and hasn't been used even in military pyrotechnics since the Nazis. Tai disease is a Japanese name coined near the turn of the century and is caused by significant cadmium pollution resulting from mining operations. So cadmium has no place in a discussion of fireworks. They say potassium is a fire hazard if there is any confinement or an explosion can occur. This is simply wrong. This is true only of elemental potassium if it is exposed to water or ignition. And elemental potassium is not used in fireworks. Sodium in elemental form is highly reactive, but you throw a little sodium into water, it damn near explodes. When heated in air, it emits toxic fumes of sodium oxide, dangerous fire hazard when exposed to heat and moisture. This is only true of elemental sodium, and elemental sodium is not used in fireworks. So what's it doing in this list? Sodium is an essential element of our diet. We ingest it daily in the form of various compounds, especially sodium chloride, table salt. New Hampshire talks about zinc. It's a human skin irritant. It affects the pulmonary system. Pure zinc powder is non-toxic to humans by inhalation, but difficulty arises from oxidation, burning, as it emits zinc fumes. Zinc is perhaps the least toxic of all heavy metals, they admit, but still can become toxic when absorbed in excess. Zinc stimulates the sensation of vomiting. An exposure to 150 milligrams of zinc can stimulate the process of vomiting in an adult. Well, if you read this, you know, you might be concerned about zinc. Well, the fact is, zinc is very rare if found at all in modern fireworks and does not represent a fireworks hazard. So again, this is very misleading. Lead. Well, they say lead affects the central nervous system. Of course it does. A poison, if ingested, moderately irritating, it can cause cancer of the lungs and kidneys, and they go on and on. Well, the fact is that elemental lead is not used in fireworks, and red lead, lead oxide, was never used commonly, has been banned in consumer fireworks, and relatively non-toxic substitutes have been used recently to replace any red lead. Lead nitrate used to be used back in the 19th century, is no longer used except possibly in some Chinese fireworks, pinwheels and Saxons, but again, very rare. Lead, on the other hand, has been extensively used in paints and in gasoline in the industry, but fireworks is clearly not a source of significant lead pollution. Magnesium, when they say, oh, magnesium is poisoned by ingestion, inhalation, magnesium dust fumes, et cetera, et cetera. Well, the fact is, the author confuses magnesium with manganese. This is inexcusable for somebody writing about chemicals. Poisoning takes the form of progressive deirritation of the central nervous system. Well, the fact is that elemental magnesium is banned in consumer fireworks, not because it's poisonous, but because it can become hot if it contacts moisture, and in rare instances can cause ignition. Metal fume fever is a condition experienced by industrial workers and welders who have chronic exposure to metal oxide fumes. It has not been associated with fireworks. And then they talk about manganese, an experimental carcinogen and mutagen, human toxicity caused by dust and fumes. None of that's relevant. Manganese is not used in fireworks. Manganese dioxide has been used rarely in the past in very tiny quantities. It's no longer used. So the authors have confused manganese with magnesium, revealing a severe chemical naivete.
Hey, Bob,
Yeah.
Bob, before you move on, we have a question from Facebook from Amanda. She has a question about drinking Moscow mules from copper cups. I think Moscow Mule is an alcoholic drink, and I assume that there's some sort of tradition or something with copper cups. Do you know anything about that or have any comments on it?
I know nothing about that. However, copper is ubiquitous in our environment in so many ways. And I don't suspect that drinking from a copper cup alcoholic beverage would be a problem, but I have to admit ignorance on that topic. Okay, nitrates. Large amounts taken by mouth can have serious or even fatal effects. Symptoms are dizziness, abdominal cramps, vomiting, bloody diarrhea, weakness, convulsions, and collapse. Sounds pretty dire. Small repeated doses may lead to weakness, general depression, headaches, and mental impairment. There's also some indication of increased cancer among those exposed. highly inflammable, and on decomposition may emit highly toxic fumes. Well, to start out with, nitrates are not highly inflammable and are generally not toxic. In fact, they are common constituents of sausages and lunch meats. They are a common fireworks oxidizer, and the most common nitrate used in fireworks is potassium nitrate, which is indeed non-poisonous. Barium nitrate is sometimes used and is indeed poisonous if ingested in quantity. Soluble barium is one of the few real toxins that occur in fireworks, and I'll talk more about that. But this comment out here about nitrate is largely incorrect. They talk about nitrites, large amounts by mouth produce nausea, et cetera, et cetera. Well, the fact is that nitrates are NO3, nitrites are NO2. They're not used in fireworks. So why are they here? I don't know. Phosphorus in phosphate. Well, this is nonsense. Elemental phosphorus is not used in modern fireworks except in very small amounts in toy caps and party poppers. And then it's red phosphorus, which is used. And red phosphorus, it is not soluble and it is non-poisonous. Phosphates are ubiquitous and found in many detergents and fertilizer and used in huge quantities in agriculture. Phosphate compounds are not used in fireworks. Sulfur. You go on about sulfates, poison to humans by inhalation in eye, skin, and mucous membrane, et cetera, et cetera. It chiefly affects the upper respiratory tract and so on. It may cause edema of the lungs and glottis and produce. Sulfates are commonly used, generally without hazard. Plaster of Paris, calcium sulfate, is sold in most hardware stores and is often used in walls in modern homes. Wallboard consists largely of calcium sulfate. We can buy sulfates in the form of sulfuric acid, battery acid, drain cleaners, some pool acids. Metal sulfates are sometimes used in sulfates in strobe composition, but they are non-toxic. Elemental sulfur is used as a common pyrotechnic fuel, but it is non-toxic if ingested. So in general, this document published by the state of New Hampshire is so inaccurate and poorly written as to be almost unbelievable. Now, I'm not picking on New Hampshire because you can find lots of examples of this kind of thing. And I'm not sure how it comes about, but I find it upsetting that this kind of stuff is out in the public realm. Okay, let's go back to some chemicals that are potentially hazardous. Ammonium perchlorate. One report listed LD50 in a rat as 3,621 milligrams per kilogram per day for 4 days. That's a lot of ammonium perchlorate. Potassium perchlorate, one report estimated an LD50 of 214 milligrams per kilogram for a 70 kilogram adult human. That would equal about 15 grams. 15 grams is like a handful. Now, these two salts are used in some rocket fuels, colored flames and stars, strobe stars, flash powders. Perchlorate, I might point out, has gained a lot of press coverage because they can persist in groundwater and have potential to diminish thyroid function in fetuses. Some effects on thyroxine levels can be noticed in adult animal studies. Neither salt, however, is considered truly poisonous. Levels found in groundwater are usually transitory and quite low. The threat appears to be more theoretical than actual. Now, that's my opinion, okay? Other people in California, there's been a big push to eliminate perchlorates because it's found in groundwater, and if it gets into the human fetus, it can diminish the effect of the thyroid gland. So it deserves some attention, I think, but I think great fear of perchlorate is unwarranted. Now, barium nitrate, on the other hand, is quite poisonous. All water-soluble barium compounds are poisonous. Now, there's one barium compound which is not water-soluble, and it's so non-poisonous it's used routinely in medicine in the digestive tract. If you have a barium enema, they give you barium sulfate, which is radio-opaque, and it lets them look at your digestive tract with an X-ray. But that's one of the few barium compounds that are non-poisonous. Barium nitrate, barium chlorate, and such are quite toxic. It's used, of course, in green-colored fires, lances, and stars. It is the only poisonous oxidizer used commonly in fireworks. However, documented instances of barium poisoning from fireworks is extremely rare. I recently read, this is not in the PowerPoint, but I recently read about dogs eating used sparklers and occasionally actually having lethal effects. So don't let your dog eat old sparklers or used sparklers or new sparklers for that matter. Now, barium chlorate used in green fires in display fireworks can be quite deadly, 0.5 gram to 5 grams for a guinea pig. And it has been used in some black snakes. And if you look up poisonings, you'll come across where a middle-aged, severely mentally disturbed man ingested 16 black snake pellets, who was eventually able to survive. Warnings about barium chlorates were mainly due to reading the dust of the salt when it was being ground. So the chemical factory that makes barium chlorate comes out with crystals, they grind it as a fine powder to be used in fireworks, and if you breathe that dust extensively, you know, you could be poisoned. The take-home messages: do not eat brilliant green stars from display fireworks. Red lead, it's PB304, lead tetroxide. This was used in the original dragon eggs, crackling stars, but has since been largely replaced with bismuth-based low toxic substances. However, you still can find some display fireworks that have red lead in them. It's a relatively rare ingredient in modern pyrotechnic formulations, and it's being replaced increasingly. Potassium dichromate, also called potassium bichromate. It's poisonous. However, it's rarely used. When it is used, it's used in very small percentages as a burn rate modifier. So it doesn't represent a hazard. So, summary. Despite a few cases in the literature, the vast majority of firework exposures are non-toxic. However, one should consider exposure to barium, arsenic, or white phosphorus as in symptomatic patients is serious. Now, you're not likely to come across this in the US. Arsenic and phosphorus are highly unlikely to be involved in the fireworks content in the US. When traveling outside the US and Canada, you are still very unlikely to encounter these elements, although it's possible. Always follow the cardinal rule. Don't eat fireworks. That may seem silly, but the fact is that fireworks do not represent a major source of poisoning. Okay, I'm prepared to take questions.
I have a question or an observation, Bob. Pete H. from Facebook. In an earlier slide, barium nitrate was listed as 350 parts per million, LD50.
No. Not per million.
ppm.
Hang on. Let's go back to that slide. I'm not sure where it is. Barium nitrate. LD50. 355 to 390 milligrams per kilogram. Is that the question?
That may have been the question, but it was written down as 350 ppm parts per million LD50. So just wanted to get a clarification of that. Thank you, Bob.
All right, I think I have a whole slide on barium compounds here. This is in regard to a 50-pound child would have to eat over 1/3 of a gram of barium nitrate. I really don't know what they're talking about. Okay, anything else?
We have a thank you. Bob, thank you for giving us late arrivals a quick review, and that was from Paul Guston. Thank you.
Okay.
Yeah, and Bob, this is Steve. I wanted to check in with you a minute here. We can go ahead and close out the PowerPoint. I get a lot of questions. People know that I talk to you often, and it's I always get the burning question. You know, we're just so well known for your glitter, and I guess very much it would be like asking the Led Zeppelin to play Stairway to Heaven again. But it's what people want to hear. So I wanted to, if you could give us tell us a second, is I know you've been working on the revising this Pyrotechnica 2. I've talked to Bob Cardwell often, and I wanted to know how that project's going. And I know that you are wanting to collect up glitter formulas from around the world. I think we have some audience members here watching today that might be able to help you all around the world. So why don't you go ahead and pose that and tell us what we can hear from you in the future.
Okay, well, I've got a lot of seminars that I'm working on, so we can maybe have other seminars of this sort, not on toxicity. But I am working on a revision of the pyrotechnic phenomena of glitter. And what I'm hoping to do in that regard is to include a lot of new formulas or different formulas. I'm not interested in having formulas that differ by a couple percentages here and there. But there are people in Mexico and Brazil and Spain and Italy and around the world, China, that are using glitter stars, and they're not necessarily using my formulas. Sometimes my formulas are used with slight modifications, but what I'm really interested in is finding formulations for effective glitter stars that are substantially different from the ones I've already published. So, you know, you can send me an email. My email address is available. I'm not sure how, Steve, maybe you can tell them that.
Well, at the end of the broadcast here in a second, we're going to provide our seminar's email address, which is very simple, and I'll forward anything they send on to you. Well, there it is now. Thank you, Joe. Yeah, if you have any questions for Bob, you can use this email address. Very easy, seminars@westernpyro.org. And then we'll pass that along. Also, at the beginning of this broadcast this morning, I mentioned that we have, I got a stack of these Pyrotechnicas 2 here, which came from Bob Cardwell. I'm very much would be happy to send you guys those in the mail, and as long as we pay Bob the money for them, Bob Cardwell, that is. And I'll figure that out. You can also email me at that address relative to that. Dr. Winokur, anything else for us this morning?
The only thing I would like to request of the listeners is that if you have questions or suggestions, don't hesitate to write to me. I'm pretty good at replying to emails, so don't hesitate to contact me if you have questions or suggestions or observations or complaints. I would be quite happy to correspond.
Okay, very good. I see one more question came up from Charlie Holloway. By the way, thank you everybody on Facebook who's dropped in questions this morning. We've had a very good Facebook audience this morning. Charlie asked, do you know the toxicity of gallic acid powder?
Gallic acid is not used very much anymore. It's quite expensive. And the short answer is no. I don't know the toxicity, but you could look it up pretty easily. And once again, it's one of these things that should be pretty easy to avoid ingesting.
Again, don't eat fireworks, right?
Yeah, I know. I know. I said that repeatedly, and it seems self-obvious, but people are not aware of dosages. You really have to eat more than a few fragments of dust to be poisoned by most anything.
Mm-hmm. Yeah. Maybe we could get Art Tilford to do a seminar on what fireworks we can eat. See how that goes. All right. Thank you very much, Bob. It's a pleasure having you on this morning. A lot of you don't know this, but I talk to Bob several times a month, and as we line up to this, maybe several times a day. Bob's been so helpful over the years in giving seminars, and our ability now to do these seminars on Zoom, on Facebook, and do these stream opens up a whole new world. Bob's got a whole catalog of PowerPoints that we can plug in from time to time, so we're gonna get those up and running. So thank you so much. Great having you on board, and glad that you're looking great. Good
Steve, thanks for all your hard work on doing this.
Sure, you're welcome. Okay. All right, let's go ahead and close this out, Joe. Next week we have, the next seminar is being given by Marcel Berner. He is one of the owners now of Pyro Digital. Pyro Digital was the founding, what do you call it, computer firing system that Ken Nixon started years ago. So he's going to be doing a seminar next week on realizing a scripted show and from concept to out to the firing site. That'll be the same time next Saturday at 9 a.m. And again, if anybody has any other seminars out there that you want to give or suggest to us, please get back to us and let us know. Again, that email address is seminars@westernpyro.org. And we'll be in touch. Thanks for watching, and we'll see you next weekend. Bye.